Okay, recording is rolling. So, welcome to another Monday, another week. You guys just turned in your simple harmonic motion and waves quiz. So, thank you for doing that. We'll tell you guys this too. Number 7, I made a mistake in the. Yeah. Okay, I think this is the last one I got. All right, so while this is on the video, yeah, this one, number 7, there's actually a mistake, so I'm going to omit this one. I hope you guys weren't working on that too long, so sorry if you were, but yeah, toss that one out and give you guys points for that. Okay. So we're moving on to these few chapters from your book. If you see a clip to the side of your desk, this page looks like this. So chapter 16, fundamentals of light, chapter 17, reflection, chapter 18, refraction, and chapter 19, interference and diffraction. So we're going to be looking at electromagnetic spectrum, optics, those topics just named there. And I want to do something a little bit different than what we've been doing the last few months, which is I'm going to alternate between I have some demos for you guys. There's some labs, there's some at-desk activities, and then those text problems just straight off the page that you guys just picked up. So we'll do a little bit of each and then just cycle around, like go back and forth there. Okay. So that's the plan next couple of weeks. Okay. Gotta switch the screen over. Okay, so start with this right here. You guys are looking at the electromagnetic spectrum. So electromagnetic spectrum is a whole spectrum of electromagnetic waves. So you have oscillating electric fields and magnetic fields. And visible light is actually one small part of this very larger phenomenon. So all these waves travel at the speed of light, which is 3 × 10⁸ meters per second. Actually, that right there, the speed of light, is the speed of all electromagnetic waves, 3 × 10⁸ meters per second. And that's also the speed of anything that's massless. So anything that does not have mass has to move through the universe at 3 × 10⁸ meters per second. Now, one thing you might wonder is, well, how do we know that value? How do we know what the speed of light is? You guys got to see a couple of perspectives on that. One of them today, and then another perspective I'll show you guys a few weeks from now. Right, so here's a visible light. This is what our eyes can detect. Right, all the colors of the spectrum are just this part right here. So longer wavelengths, shorter, smaller frequencies, that's closer to red, and then shorter wavelengths, higher frequencies is closer to violet, and all colors in the middle. Now, some animals can see a little bit into the infrared part of the spectrum, or a little bit in part of the UV part of the spectrum. Right, so certain like insects, birds, different kinds of animals have different kinds of eyes, can see a little bit more there. So that's why there's certain, say, patterns on flowers or butterflies that you can only see under like in UV light or in infrared light, something like that. So getting longer wavelength, got infrared, right? That's like beyond the red, and then microwave. So yeah, like microwaves in your microwave oven, those are EM waves, just with a very long wavelength of a few centimeters. Notice this order of magnitude, 10 to the minus 2 meters, which is like a centimeter. So anything's a few centimeters. And then anything longer than that, let's say like a meter and longer, could be radio waves. If you tune into an FM station right now, let's say like 90 something point something, right? Those radio waves are approximately 3 meters long. You think it's about 3 meters long, be a radio wave. Right. Then the other way, so if you go to violet and then increase the wavelength from there, or sorry, increase the frequency, I should say, decrease the wavelength. Right? You guys know speed equals wavelength times frequency. All these waves are moved at the same speed. That got ultraviolet, then X-ray, and then gamma ray. Okay. Now, one thing I think is kind of interesting is that even though all these waves travel at the same speed, and really a similar phenomenon, they actually travel through different materials differently. I mean, this is just one little tidbit about these. So, for example, we're surrounded by a bunch of walls that are blocking visible light. Okay? So, why can't we see the next classroom? Well, because visible light cannot travel through these walls right here. What about other parts of the spectrum? Like, can radio waves travel through these walls? Well, if you had a radio, I bet you could tune into a radio station. So, interesting. If it's a long enough wavelength, you can go through the material that makes these walls, but not visible light. Right? Maybe some of these other parts. Oh, hey, maybe except for that glass window right there. I can see through that glass window. Visible light can go through there. Why is that? Well, hang tight on that. It's one of the very last things I'll tell you when we get to quantum mechanics. But that glass will block infrared and UV. So, what what parts of the wave can go through, what parts of the spectrum can go through what materials. Okay. Let's talk about colors. So let's focus on this this visible part of the spectrum. Hey, if I wanted you guys to paint a picture, I said I'm going to give you guys just a small handful of colors, I don't know, maybe 4 or 5 colors to paint with. And you're thinking, well, I sure would like to paint something with like lots of different colors. Maybe I could mix some colors together. What would be some good colors to choose for like pigments? What do you guys think? Yeah, primary colors, right? So you might think something like red, yellow, blue, right? Actually, I'm going to shift that a little bit. Like red, yellow, blue is a good answer, but slightly maybe more technically correct answer might be a magenta, yellow, and cyan. That's kind of close to red, yellow, blue. Now, magenta, yellow, cyan, those are actually the colors in your color printer. So if you buy, say, like a color ink cartridge or like the individual pigments, those are the colors that you would have. What about this though? A little bit different question. If you look at your phone screen, let's say you could zoom down like microscopically, or your TV screen or computer screen, phone screen, there are only 3 bulbs that actually light up. Do you guys know what colors those are? What bulbs actually light up on your screen? Red, blue, and green. Yeah, it's called RGB standard. Let's do a quick Paul Hewitt here.
Hi gang, color physics. You see me in full color, not because of a white light shining on me, but because of 3 lamps, a red one, a green one, and a blue one. And all these 3 colors mishmashed together to give the same effect as white light. Let's look at these one at a time. Put the red lamp on, and I have a shadow. Of course, the shadow is black because no light's hitting there. Let's try 2 lamps. That black shadow turns out to be green because now we have green and red shining. And the green lamp casts a shadow which is not black, but is red. That's because a red light's hitting it, huh? Let's try 3 lamps, red, green, and blue. Now we get 3 shadows. This is no longer green, it's greenish blue. This is no longer red, it's reddish blue. And this is yellow. And yellow turns out to be the average of red and green. And if I overlap these, I can get all kinds of nice colors. And bear in mind, all these colors you can see are the result of only 3 colors, red, green, and blue. Those are the colors of your TV set. TV physics, physics all around you. Yay.
Yeah, so that might remind me of this right here. You're seeing refraction. We're going to talk about refraction in a couple of days, but yeah. So you have like some glass surface and some ray of light going in, like ray of white light. Each wavelength of light will refract at a little bit different angle. That's why the colors spread out like this. Right, so red doesn't refract as much as say blue does. Isaac Newton was the first person to figure out that white light is actually composed of all the colors, just like Paul Hewitt was showing you. If you have a red, green, and blue lamp, they'll make a white light if you put it all together. The cones in your eyes that can detect colors, we each have 3 different kinds of cones. You have a red cone, a green cone, and a blue cone. Dogs, I want to say, only have 2 of them. I think the blue and the green one is what dogs have. And some animals have more than 3 different kinds of cones. So humans have red, blue, green, and then you can make all colors. Now, this is with additive color mixing. Now, that's different from the pigments that I was talking about. Like, as I said, if you paint a picture or like from your ink printer, that is sort of like the opposite of this. So what you guys are seeing right now is additive color mixing, right? The more color you add, the more it gets to white light. Like white light is all the colors put together. Yeah, Isaac Newton was the first person to figure that out. And then if you take away all the lamps, well, that's how you get black. That's like the absence of any color. Right. So what about the story I started with, like trying to paint the picture? So like painting a picture, for if you have say red and yellow, for example, and you make those together, that would be orange. That's not what's going to happen with these lamps though. So like pigments or paints, that's subtractive color mixing. And it's subtractive because the more color you add, the more different kinds of wavelengths that it absorbs. So yeah, pigments will absorb everything except for the color that they are, and they'll reflect that back into the world. So if you, let's say you had red paint and yellow paint. So red paint is absorbing everything except for red, yellow is absorbing everything except for yellow. You mix those together, they absorb everything except for what's in common between them, and that'd be sort of like an orange color. But if you keep adding more paints, like I mean, some blue paint, some green paint, some purple paint, and you just add it eventually becomes like a mucky, like brown, dark brown kind of color, because now it's just subtracting all the light colors. So yeah, so recap, what you guys are looking at right now is additive color mixing. It's the same thing as your phone screen. And if you're working with like paints or pigments or color printer, that's a subtractive color mixing. That's right there. All right. Switch over Yeah, I do have a lot of cool demos and activities lined up for you guys this week, but I'll save some of those for another day. Right now, let's do this. Oh, hold on. Yes. Actually, before I get going too far, I did forget one thing here. Switch the screen back. Get something. Share. Whatever just happened. Stop share. All right. I don't know what it is. Okay. Share screen. To share. Okay. Do you guys remember way back in August? This goes way back. I was telling you, well, how do you measure things? How can you quantify and measure things? For example, a push or a pull could be a force. Well, maybe you can measure that in pounds, that'd be okay. But in the metric system, maybe you would use newtons. But a newton is really a composite unit. It breaks down into kilogram meter per second squared. Okay, so what are like the fundamental ways to measure things? Well, kilograms, meters, and seconds are three of those, right? Kilograms for mass, meters for some displacement, and seconds for time. Those you can't really subdivide. Right? And there are 7 fundamental units altogether. All throughout fall semester, we pretty much just took these top 3, kilograms, meters, and seconds, and rearranged them all different ways to get newtons, joules, pascals, watts, right? All those were some combination of kilograms, meters, and seconds. Let's take a look at these other ones. So moles, you pretty much use in chemistry. Now mole is just a really big number, so it's kind of just like counting things. Ampere for electric current, that's going to show up in this class a few weeks from now, so we're eventually going to get there to electric current, do some circuits. Kelvin to measure temperature, that's also coming up pretty soon in a few weeks. But the new one I'm introducing to you guys today is this one right at the bottom, candela, to measure luminous intensity, candela. So if you want to quantify how bright is something, how bright is that bulb, how bright is that star in the sky, is the brightness fluctuating, how can we quantify that? If we get something with candelas, right? Now, switch back. Don't do this hardly ever, but I want to read a few paragraphs from your book, because there are 3 very similar type terms of luminous flux, illuminance, and luminous intensity. So yeah, let's switch the screen back. Okay. Let's go over those. What are the definitions of these things? How do you think about these? Okay, so this is on page 433 of your book. I did have a class set of books, or the PDF that is posted to Google Classroom if you want to access it there. And so quantity of light, right? How much light? How bright is something? The rate that light energy is emitted from a luminous source is called luminous flux. The variable is going to be capital P. We're going to use an equation later that'll show up. The unit of luminous flux is the lumen. I know it's not candela. We're going to work towards candela. So one thing at a time here. A typical 100-watt incandescent light bulb emits approximately 1750 lumens. So a really bright bulb, say from like the old style, like 20 years ago. If you can think of the luminous flux as a measure of the rate that light rays come out of a luminous source. Imagine placing a light bulb at the center of a 1 meter radius sphere, like you see right here. See the sphere? There's a bulb right in the middle, and the sphere has a radius of 1 meter. The light bulb emits light in, okay, let's say all directions. It's like a point source. The 1750 lumen of luminous flux characterizes all the light that strikes the inside surface of the sphere in a given unit of time. So even if the sphere was 2 meters in radius, suppose you blew this up to like twice the radial size, the luminous flux of the bulb would still be the same as it would be for the 1 meter radius sphere, because the total number of light rays does not increase. So when they talk about luminous flux, they're talking about some constant quantity. It doesn't matter. So if you get further away, it might appear dimmer, or if you get closer, it might appear brighter. That has nothing to do with this, right? Luminous flux is sort of like a constant value per source. Right? Now, what about this other idea? Once you know the quantity of light being emitted by a luminous source, you can determine the amount of illumination that the luminous source provides to an object, such as a book. The illumination of the surface, or the rate that light strikes the surface, is called the illuminance, and the variable is capital E. Think of this as the measure of the number of light rays that strike a surface. Illuminance is measured in lux, which is equivalent to lumens per square meter. Okay, well now it's starting to matter like how far away you are, right? So as you get further away, it appears dimmer, right? Or don't look at the sun, but if you did, it'd be crazy bright, right? But you can look at stars out in the night sky because they're so far away, it just don't appear as bright. That's sort of the idea of luminance, right? The further away you are, the less bright it appears. Right? Consider the setup in this figure. Right? So we're back to this 1 meter radius sphere. What is the illuminance inside the surface? The equation for the area of a sphere is 4 pi r squared. Okay, so now we're bringing in some geometry. So for area of a circle, or sorry, a sphere, area of a sphere, surface area is 4 pi r squared. And if this particular sphere has a radius of 1 meter, then wouldn't the area just be 4 pi square meters? Because 4 pi times 1 meter squared. The luminous flux striking each square meter is 1750 lumens from that light bulb, divided by 4 pi square meters, or 139 lux. Here could be like a square meter broke off, actually like a square meter. At a distance of 1 meter from the bulb, which is anywhere on this inside surface, 139 lumens strikes each square meter. So the illuminance would be 139 lux. Okay. Okay. Now, this is what if you were to change your distance from that point source though? Okay. This is where the inverse square law comes back in. You guys know about the inverse square law because you guys remember studying universal gravitation. Remember, if you're like twice as far away from some object, you get a quarter of the gravity force. And if you're 3 times as far away, you get 1/9 of the gravity force. I did play a Paul Hewitt video for you guys back in the day, and he was actually using a candle as an example of this. But the fact that we live in a three spatial dimensions universe will set up the inverse square law of relationship. So same thing with light. If you're at some distance, say you catch so much light, if you double that distance, you get a quarter as much. If you do 3 times that distance, then you get like a 1/9 as much light. That's an inverse square law. I'm going to skip on down to luminous intensity. Okay, now here's where candelas come in. So some luminous sources are specified in candela, CD. That was that unit that you guys just saw on that graphic. A candela is not a measure of luminous flux, but of luminous intensity. The luminous intensity of a point source is luminous flux that falls on 1 square meter. Thus, luminous intensity is luminous flux divided by 4 pi, right? Because it's kind of like always being stuck inside this the sphere. So a bulb with 1750 lumens of flux has an intensity of 1750 divided by 4 pi, which would be 139 candelas. Okay, so kind of like the idea of flux, but just divided by like per unit area. Okay, so then we got a lamp and a candle, and there's some distance from some screen. One of the textbook problems coming up that we're going to solve later today is going to be a set that looks pretty similar to this. Okay? So there's some light landing on the screen from the lamp. There's some light landing from the candle. All right, so you guys get that? Look at here. All right, now to these this page. All right, so I put a few formulas up here. I'm gonna go over what each of these means so that we can know the context for what we're about to set up. All right, so this first one was the one that we've just been looking at. So that says that the luminance. The luminance is equal to the luminous flux divided by 4 pi r squared, where r is your distance from that point source. So the further away you get, the less the illumination for some constant luminous flux. Okay. What does this next one say? Okay, this next one, we find this in the book too. This up here is called Malice's law. So So here's Malice's law. Oh, hey, if you have a couple of polarizing filters, how much light's going to get through? So I've got this demo lined up for you guys right here. Got some polarizing filters. You guys remember these polarizing filters from last week? Right. So they'll polarize light in one direction. Let's say this is like horizontal and horizontal. So if I go horizontal and horizontal, okay, all the light gets through, no problem. But what if I turn this guy 90 degrees? Ooh, look, it blocks all the light because now it's horizontal versus vertical. Remember that this is evidence that light is a transverse wave because you can polarize a wave only if it's transverse. Interesting. So all the light gets through, no light gets through. But what if it's like turned like this, like 30 degrees or 60 degrees? Well, I guess that would be 30 and this would be like 60, right? And then 90. Right? How much light's getting through, say, at the like a 30-degree angle difference? Well, that's what this is for. So here's like say the total light that's being emitted, right? How much gets through each screen, right? Well, or let's say through both screens, right? It depends on the square, the cosine of the angle between them. Show you guys take guys a quick recap of sine and cosine on a unit circle, and we'll run a couple of examples and see why that makes sense. Okay? So this could be a unit circle. You guys learn about this maybe in pre-calc or trig or something like that. Traditionally, you put 0 degrees here and you work your way counterclockwise around. So here's 90 degrees, here's 180 degrees, here's 270 degrees, and then back to 360 degrees. Right? You just keep counterclockwise. Okay. So if you had a 30-degree angle, that might look approximately like that. This might be 30 degrees, for example, from the x-axis. Right? So sine of an angle tells you how far up or down on the circle that you are, and cosine of the angle tells you how far to the right or left you are on that unit circle for some particular point. Let's look at these different points. Got it marked out. Actually, we're mostly interested in just this first quadrant, just 0 to 90 degrees. Okay. So let's say 0 degrees. That would be like exactly right here. Here's 0 degrees. Right? What is sine of 0 degrees? Should also be 0, right? Okay, let me check that. Sine of 0 degrees is 0. Okay, so you're not up or down from that point. Right? So you're just right on the axis. Okay. What is sine of 90 degrees? That's 1. Because if this is a unit circle, so you'd be like 1 unit up. Okay. How about sine of 30 degrees? Do you guys know that one? It ends up being exactly 0.5, which means this 30-degree angle should correspond to, see how that's like halfway up, halfway up. Okay, that's sine. But this formula we're looking at had something to do with cosine. So let's check out cosine. What is cosine of 0 degrees? 1. You see 1? It's like 1 unit to the right. Okay. What is cosine of 90 degrees? Well, that's 0, right? Because you're not to the right or left from the y-axis, right? That would park you right on the axis. Right? Okay. Now, how does that align with this formula? Well, cosine of 0 degrees would be 1. If you do 1 squared, that is also 1, which means you let 100% of the light through. Oh, okay. So those two polarizing filters are at 0 degrees from each other, like horizontal, horizontal. Yeah, all the light gets through. What if you pop in 90 degrees? Well, it's cosine of 90 degrees is 0. 0 squared is still 0. So none of it gets through. That's that situation at right angles. Okay. And then if you want anything in the middle, like at 30 degrees, then you could just pop in 30 degrees. Cosine 30 degrees is like, what is that, root 3 over 2, I think? And then square that. And then that will tell you the proportion of light that actually gets through. This formula right here is actually a rearranged formula of something that you guys have been working with the last couple of weeks. If you multiply up frequency, you get speed is equal to wavelength times frequency. Right? Been working with that for a while now. This is a special speed though. Whenever you see lowercase c, that means the speed of light, right? Which is what we're talking about next couple of weeks. Then this next one, that almost looks familiar. Doesn't this also almost look like Doppler shift? Right? the observed frequency is equal to the source frequency multiplied by some ratio. That's actually what this is. This is Doppler shift. But it's a special kind of Doppler shift. It's referring to, let me switch my screen back over. I want this one right here. Yeah. It's talking about red shifting and blue shifting. You guys know what red shift and blue shift is? So let's say you're looking up at the sky. This is actually something that Edwin Hubble came across about 100 years ago. Edwin Hubble was looking his telescope into the sky and getting really precise measurements on what the light was coming off distant galaxies. And notice that pretty universally, the galaxies were kind of red shifted. All the light coming off them was a little bit closer to the red part of the spectrum than it should have been. In fact, the further away the galaxies were, the more they were red shifted. That was some of the first evidence that we had that the universe was actually expanding, right? Because the galaxies moving away from us. So the faster and further they are from us, and the two go hand in hand because of cosmological principle, how the universe expands, then it's kind of like the ways we get stretched out away from us. It's a Doppler shift, but in terms of light, and so it gets like more red shifted. Right? Now, the opposite is true, that if something is more blue shifted, that's an indication that's moving towards you, or something is moving towards you in a hurry. The wave is going to get kind of crunched up, decrease the frequency, it's going to become blue shifted. There is at least one galaxy that is blue shifted compared to us, and that's the Andromeda galaxy. So so one day the Andromeda galaxy is going to crash into the Milky Way, and we know that because of this fact right here, red shifting, blue shifting. Okay. So back over here, okay, that is this Doppler shift right here. Okay. And then this last equation is also a Doppler shift, but it's in terms of wavelength. See, this one's in terms of frequency, this one's in terms of wavelength, but okay. So these two both have to do with red and blue shifting. Okay. All right, let's take it to these questions. Number 56. Okay, now number 56 is a really exciting adventure. There was this Danish astronomer, Ole Romer. I don't know that I'm pronouncing his name right, but I'll just call him Ole Romer. Found that the average increased delay in the disappearance of Io from one orbit around Jupiter to the next is 13 seconds. Okay, and then it breaks into these questions. What are they talking about? Right, something about the orbit of Io. What? So the story that goes along with this is this is one of the first ways that actually I think it may be the first way in history that the speed of light was calculated, and it wasn't with a ton of precision, but you guys know that the speed of light is 3 × 10⁸ meters per second. Now, the first time this was founded with about at least that much precision was in 1849. But the story, we'll save that story for another day. But the story that we're doing right now, this guy made the first calculation for the speed of light, and he came up with 2.2 × 10⁸ meters per second. Oh, yeah, go ahead.
Isn't also like the two-way speed of light?
Well,
Is also two-way speed of light.
yeah, there's this. Yeah. Okay. Yeah. So, tell me. I'll tell you what the setup was for the story, and you see sort of how he figured this out and put this together. So he actually got it pretty close. How did he do this? Well, he was looking at the planet Jupiter, and so draw Jupiter way off in the distance here, big old red spot, and he was watching. Now, this goes back a few centuries ago, so you can look through a telescope and see moons going around. I think you can see like four biggest moons, I want to say, with the telescope, a few centuries ago. And one of them is a moon called Io. So here's Io, here's Jupiter, right? And you can watch Io go around and watch its orbit. Okay, so it takes so long to go around. Right? Now, here's where you have to. You guys ready to think abstractly? Let's do get like orbit of Earth. Okay, so here's Earth. Right? Okay, so we're thinking real big picture on this, right? You guys got your brains turned on? Okay, so here's Earth, sort of headed towards Jupiter. Okay? And the fact that Earth is moving towards Jupiter means that, well, the distance between Earth and Jupiter is getting closer, closer, closer. Right? And there is a finite speed of light. Nobody knew back in the day exactly what it was yet, but he's about to find out using something to do with this. Right? So distance equals speed times time. So as that distance closes, it should take less and less time for the light to reach Earth, right? This guy was watching the orbit of Io. It takes about 42, 43 days, something like that. Or wait, no. Hours. It takes about 42 hours. Okay. But he noticed that the time was inconsistent. So while Earth was sort of heading towards Jupiter, that time decreased for one orbital period by about 13 seconds. 13 seconds compared to like a 42-hour round trip. Huh. Okay. But then when Earth was heading away from Jupiter, it was like the opposite was true. It seemed like it took Io a little bit longer to go around Jupiter, like plus 13 seconds. And while Earth was passing, maybe it was something closer to the like see truly what was happening. Now, why did it look like Io was going around Jupiter a little bit too fast and then later on a little bit too slow? Because Io wasn't changing what it was doing at all. Like if you just sit there stationary, you just see go around, like you have the same time to go around. Right? Well, this Danish astronomer realized that he puts two and two together and realizes he can actually use this to calculate the speed of light, because light has a finite speed, and the fact that you're closing that distance, getting closer to it, or opening up that distance further away, that the information that the light carries also would either reach you faster than it should or slower than it should. Okay, so let's just go through the book problems, like as they set it up. Now, the way that your book takes you through it is sort of backwards of how he did it, because the first question here says, how far does light travel in those 13 seconds, like that 13-second difference? So we're working back from knowing what the speed of light is. He was trying to figure out what this number was. So we're sort of solving it backwards from what he was doing back in the day. But let's do it. So we got 56, part A, distance equals speed times time. And notice I put a special speed, the speed of light, that's what C is. So distance, that's what we're solving for. The speed of light is 3.0 times 10 to the 8 meters per second. We know that because we're in the future. And time was 13 seconds. So put that all together. That's 3 times 10 to the 8, all times 13. I'm looking at 3.9 billion meters. Right, 3.9 billion meters. Okay. Let's hold on to that number. So in 13 seconds, that's how far light travels. Part B says each orbit of Io takes 42.5 hours. Earth travels that distance calculated in part A in those 42.5 hours. Right? So for Io to make one orbit, Earth, how far does Earth travel? Well, we're watching a 13-second difference. Right? Here, let me draw you guys a little bit different picture. Okay, so I drew you guys this picture before, right? Like this. Right. Let's get a close-up of Jupiter, but from the top. So here's Jupiter from the top, right? And here's Io going around Jupiter, something like that, right? Oh, back up, you guys can see this, okay. Like that. Right. So as Earth was headed towards Jupiter, it looked like Io was going around too far, and as it was going away, it was like there was this gap, like it wasn't quite completing its orbit, but it always missed it by like 13 seconds. So part B, we're going to say find the speed of Earth in kilometers per second. Okay. So what's the speed of Earth? Okay. Well, it would have gone this distance, 3.9 times 10 to the 9 meters, right? Now that's how far light travels in 13 seconds. That's how far the Earth would have gone in the time it takes Io to make one round trip, which was 42.5 hours, right? That be true? Okay. Now this would be meters per hour. That's kind of crazy. But let's change that to kilometers per second. Kilometers per second. I'm going to open up a dimensional analysis table to convert this to kilometers per second. I should have given myself more room, but I think I can squeeze it in here because I know that 1,000 meters is 1 kilometer. And I know that 1 hour, I could say 60 seconds, sorry, 1 hour, 60 minutes 1 minute, 60 seconds. I'm just gonna show that together, make that 3,600 seconds, like that, right? Yes, this dimensional analysis table. Okay, so hours, meters, kilometers per second. So I'm about to calculate the speed of Earth using this crazy IO method in kilometers per second. So it's 3.9 billion, all divided by 42.5 times 1,000 times 3,600. I'm looking at 25.5 kilometers per second. Okay, so that could be the calculated speed of Earth using this crazy method of we're watching Io go around Jupiter. Where are we going with the story? It seems like we're kind of off in the woods here, but those guys all going to come together. Part C says, check, make sure your answer in part B is reasonable. Calculate Earth's speed in orbit using orbital radius and time period of 1 year. Okay, so here's orbital radius of Earth's orbit. 1.5 times 10 to the 8 kilometers. That is also called 1 astronomical unit. If you ever hear 1 AU, 1 astronomical unit, that's the distance from Earth to the sun, which is this number right here. So you could use this to figure out the circumference of that orbit. And if you divide that by a time period of a year, like 365 days, that can also give you something that you can compare to this number. Hopefully it's like the same answer, right? So let's figure that out. So the speed of Earth from a different point of view is equal to circumference equals 2 pi r divided by time period t of 1 year, right? So it's going to be 2 pi times radial size of 1.5 times, you know what, saying 10 to the 8 kilometers. No, sorry. No, let's do that. 10 to the 8 kilometers. Okay. Divided by time period of, I'll go ahead and start with 365 days. Maybe I'll do a little dimensional analysis down here. Right, all in this denominator. So, okay, 1 day, 24 hours, and 1 hour, 3,600 seconds. Right, so if I divide this out, what is 2 pi? So 2 pi r to get the total distance Earth moves in one orbit. 1.5 times 10 to the 8 kilometers, all divided by 365 by 24 by 3,600. I'm looking at 29.9, and the unit would be, of course, kilometers per second, because this is set up so that hours goes away, days goes away. We got kilometers per second. Okay. Hey, look at this number compared to this number. They're about the same thing. They're really, really close to each other. What is that divided by 25.5? They're only off by about 17%. Yeah, that's really close. Okay. Now, the process that we just went through, here's how it connects to what old Romer did back in the day, is he was able to do this part C, get a pretty good estimate of what this was. Okay? And then he worked backwards from there to calculate the speed of light. And that's how he got something that was like for this number, like 2.2 times 10 to the 8 meters per second. Okay. Pretty close to 3.0 times 10 to the 8. All right, there you go. Questions on that one? Okay, so that's a deep thinking type problem there. Right? So just like usual, as long as you guys are following along with me and doing all these, then when I eventually pick this up, then I'll give you guys credit for that. It'll probably be like sometime next week. Number 57, student wants to compare the luminous flux of a light bulb with a 1750 lumen lamp. The light bulb and the lamp illuminate a sheet of paper equally, but the lamp is 1.25 meters away and the light bulb is a little bit closer, 1.08 meters away. What is the light bulb's luminous flux? Ooh. So let me draw this out, 57. So we got, do a horizontal axis, say they're all very well aligned here. Okay. Let's get a sheet of paper right about there. Let's have a lamp. and on the other side, a light bulb. Okay. Now they're both shining, but they're different distances from the paper. So the lamp was given as being 1.25 meters away, and the bulb was 1.08 meters away. Okay. Now, if they are illuminating the paper the same, say if you're an ant crawling around on this paper, you look at the lamp, say, how bright is that? And then you crawl on the other side and look at the bulb, and it's like, oh man, that seems like equally bright. Okay. That means that if you were, say, like exactly a meter from each, say like 1 meter and 1 meter, which of these light sources is actually the brighter light source with a greater luminous flux? It's got to be the what? The lamp or the bulb? Who's actually brighter at the same distance? It's got to be the lamp. The lamp's got to be brighter. Because here, let's go back to the scenario because you guys aren't close. Okay? But the fact that the paper is closer to the bulb, but they're both illuminating the paper the same, the lamp has to be brighter, say like from 1 meter out versus 1 meter out. But what's the equation that's going to connect together? Well, it's illuminance is equal to luminous flux divided by 4 pi r squared. Double check something here. What's the luminance? Yeah, 4 pi r squared. You guys remember 4 pi r squared is the surface area of a circle. Okay. Oh, and the luminance is the same from each object on that paper. So E from the lamp is equal to E from the bulb. So luminous flux from the lamp divided by 4 pi r lamp squared is equal to luminous flux from the bulb divided by 4 pi r bulb squared. Okay, good that. Guys got that? Okay. And then, okay, 4 pi is going to cancel. So even if you missed the 4 pi part, that's okay, because it really just comes down to a proportion. Okay? And we know 3 of these 4 values. They told you that the luminous flux from the lamp was 1750 lumens. So 1750 lumens divided by this distance of 1.25 meters being squared, because inverse square law, right? Inverse square law is equal to luminous flux of the bulb that we're solving for divided by 1.08 meters being squared. Okay. So cross multiply this value, and then you'll get your answer. So it's 1750 lumens times 1.08 squared divided by 1.25 squared. I'm getting P bulb equals 1306 lumens. Okay. You guys can do that? Guys good stuff? These other 4 questions from chapter 16 are all about astronomy, looking at galaxies, something about Doppler shift. Let's start with something pretty fundamental here. What is the frequency of oxygen's spectral line? Ooh, I need to tell you guys about spectrometry. If its wavelength is 513 nanometers, right? So every element, light shines on it. There are certain frequencies and wavelengths of light that will be emitted from it. And you can use this method to figure out what is the composition of a star, like how much hydrogen is in it, what's the composition of an atmosphere or some distant planet. Okay, so in this case, let's say we're focused on this oxygen molecule. You know the wavelength, can you figure out the frequency? So I know number 14, that speed equals wavelength times frequency. Of course, we've got a special speed, so speed of light. We're solving for this frequency. So wouldn't frequency be equal to speed divided by wavelength? So frequency is equal to 3.0 times 10 to the 8 meters per second. Divided by wavelength, it says 513 nanometers. Guys, nano, that's 10 to the minus what? Minus 9. So 10 to the minus 3 is milli, 10 to the minus 6 is micro, 10 to the minus 9 is nano. So this would be meters. So that divided by that. 10 to the 8 divided by 10 to the minus 9. Isn't that like 10 to the 17? See, what's 3 over 513 times, 3 times 10 to the 8 divided by 513 times 10 to the minus 9. Okay, and then that fraction makes the number smaller. 5.85 times 10 to the 14 hertz, because we're talking about a frequency, so that's got to be in hertz. Okay. All right, so that'll be a pause point today. Tomorrow we'll finish those other questions and then move on to reflection and mirrors, and we'll do some ray diagrams tomorrow. Okay.